Okay, section 9.8 deals with implicit differentiation. So this is what you have to do if a function that you are dealing with is not written in y equals f of x form or x equals f of y form. So in those situations when it's impossible to rearrange it, or it's after rearranging it, it's really difficult to differentiate it, you need to have a way of differentiating the functions, and then it's called implicitly. Otherwise, that would be an explicit differentiation. So the way you do it, you apply the chain rule. So for example, if I'm differentiating f of y, so a function in terms of y, you're kind of imagining that inside every y there will be x's. So you're going to differentiate your function f, so whatever that differentiates to, and you follow it by the inside function differentiated with respect to x, so by dy dx. There you go. So you have to differentiate the outside function, follow it by dy dx, which is differentiated inside function. So over here, if you've got y to the power of n, then you apply the normal rules for the power function. So the power comes down, reduce the power by 1, but then you need to follow it by the inside function differentiated. So that y differentiated is dy dx. If you have a product, and that's one of the easiest products, so you've got a mixture of x's and y's, then you simply apply the product rule. So imagine u is equal to x and v is equal to y. Then u dash is simply 1, but v dash y has to be written as dy dx, because imagine inside y there are x's. And then you multiply vu dash plus uv dash. So vu dash is going to be 1 times y, so it's y. Let's just quote the product rule as well. So it's vu dash plus uv dash. Always a good practice to quote it. And then x times dy dx. So remember, if it's a product of any kind, it could be y squared times y, it could be x times sine y, you have to apply the product rule. So let's see if we can have a go at example 21 onwards. So in this example, as you can see, there is a function. We simply need to differentiate it as we go along. So it's really, really simple. Okay, you start with x cubed. That is a function of x. It will go to 3x squared plus, because there's a plus, x differentiates to 1. Y cubed goes to 3y squared, but then imagine inside your y there are x's, so you need to follow it by dy dx. So as soon as you hit a function of y, you need to follow it by dy dx, plus 3y goes to 1 followed by dy dx, equals, because there's an equal, constant differentiates to 0. Now we are asked to find dy dx in terms of x and y. So here we've got to separate the terms that involve dy dx. So keep them on one side, put all the other terms onto the other side. So it's minus 3x squared minus 1. Factorize dy dx, and you will have 3y squared plus 3 equals to minus 3x squared minus 1, and then divide by the bracket that dy dx is multiplied by to get 3x squared minus 1 over 3y squared plus 3. You can also bring that minus in front of the bracket, factorize it out to get 3x squared plus 1 left, and you can even factorize the bottom, 3y squared plus 1. There you go. So this is dy dx in terms of x and y. If you're ever asked to evaluate it, you will need to have the coordinates of points, both x and y coordinate, and use them in this answer. Okay, so the second example, again, we need to find dy dx. And this time we find the value of the dy dx at the point with x coordinate equals 1, y coordinate equals to 1 as well. So, first of all, you can see that it's the first term you hit is made out of the product. So you're going to use the product rule. uv dash is equal to uv dash plus uv is going to be equal to vu dash plus uv dash. So your u is for x, so u dash is for v is y squared, v dash is 2y followed by dy dx. Remember, we are doing implicit differentiation. So this half of your expression will go to vu dash, so this times that, 4y squared plus these two times together, so it's 4x multiplied by 2y dy dx. So that's this part over here. Using the second part, we are going to use the quotient rule. So the quotient rule is going to be u over v dash. That's going to be v u dash minus u v dash over v squared. So u is equal to the numerator, 6x squared. Let's differentiate to give you 12x. V is the denominator, so that's y, differentiates to dy dx. Let's combine these into the correct expression. So v squared goes in the bottom. On the top, we're going to have v times mu dash, so 12x times y, minus these two times together, so it's 6x squared dy dx. So this is the second part, and all of that is going to be equal to whatever 10 differentiates to, which is 0. Okay, so let's now put them together so they just look a bit more tidy on one line. So this is 4x times 2y, so it's 8xy dy dx plus 12xy minus 6x squared dy dx over y squared equals 0. Okay, we are asked to find the value of dy dx at the point where x is equal to 1, y is equal to 1. So there's no need to rearrange everything to make dy dx the subject and then substitute x and y coordinate into that. Let's substitute the x's and y's first and then rearrange it. It will make our job a little bit easier. So if you put, instead of y 1, you'll have 4. If you put, instead of x and y 1, you'll have 8 left, dy dx. Plus, on the top here, you will have 12 times 1 times 1, so 12, 6 times 1 dy dx, all over 1. So you will have 8 dy dx minus 6 dy dx, so it's 2 dy dx, plus 16. So dy dx is equal to minus 8. And that's the answer. So just one more example. Example 22. I didn't want an example. So let's have a look. This time we are going to find the value of dy dx, again at the point where x and y coordinates are equal to 1. So we need to differentiate this implicitly, because you can see there's no way we can make y or x the subject. So the first term on the left hand side is the product uv. Let's quote the product rule, vu dash plus uv dash u is going to be e to the power of 2x. That differentiates to 2. Okay, so applying the product rule, u is going to be e to the power of 2x. A u dash is 2e to the power of 2x. V is ln y, so v dash goes to 1 over y, must be followed by dy dx because we are going to differentiate implicitly. Let's combine these terms to create the left-hand side of our answer. So it's going to be vu dash, so 2e to the power of 2x multiplied by ln y, plus uv dash, so e to the power of 2x multiplied by 1 over y dy dx equals x going to go to 1, y is going to differentiate to dy dx, and 2 goes to 0. So at this moment we're going to substitute x equals 1, y equals 1. So we are going to obtain 2 to the power of e squared. So e to the power of 2, so 2e squared ln 1 plus e to the power of 2 plus 1 over 1 dy dx is equal to 1 plus dy dx. So this will go to 0 because ln 0 is equal to 0, so the whole thing will be 0. And here we've got e squared dy dx is equal, let's just take away dy dx from that, so we put all the dy dx's together, is equal to 1. Factorize dy dx to be left with a e squared minus 1 in brackets equals 1, giving us dy dx equals to 1 over e squared minus 1, and this is the value of the gradient in the exact form, the exact answer, so not rounded. You put them in the calculator and evaluate it if you wish, but usually we'll leave it in the exact form. So that takes us to exercise 9H on implicit differentiation.